Some of the most elegant tools in programming hide a massive amount of mechanical friction just beneath the surface. Take the Python for loop. It's one of the first syntax structures we learn, and it's so readable that most developers use it without a second thought. You type for char in golf, tell it to print the character, and the terminal instantly outputs G, O, L, and F one by one. But this readable syntax is a facade. It is syntactic sugar wrapping a strict object-oriented mechanism known as the iteration protocol. Peering beneath this facade to the protocol itself allows us to leverage Python's internal mechanics for managing data more efficiently. To truly understand this protocol, we have to strip away the syntax and watch exactly what CPython is executing under the hood. When you run a for loop, the first thing Python does is attempt to create an iterator. It silently calls the built-in iter function on your target object. Next, it sets up an infinite while loop. Inside that loop, it repeatedly calls the next function to extract values from that new iterator, step by step. To know when to terminate, the loop waits for the iterator to run out of values and raise a stop iteration exception. It catches that exact error and safely breaks the execution. Every single time you write a basic for loop, Python is silently orchestrating this exact while, try, except sequence just to manage the state of your data. This brings us to a mechanical distinction that trips up a lot of developers. What exactly is that iter function producing? We need to separate iterables from iterators. An iterable is any passive data container. Strings, lists, dictionaries. If it implements the __iter dunder method, it is an iterable. But an iterable only holds data. It has absolutely no concept of internal state or sequence tracking on its own. An iterator is the stateful agent generated by that iterable, implementing both the _iter and _next methods. Think of it as a bookmark. It maintains internal state, remembering exactly which item it just processed, and knowing exactly where to resume. While an iterator is technically also an iterable, because it returns itself when passed to itero, a standard passive iterable, like a list, is never an iterator out of the box. It is common to assume that because you can loop over a string, the string itself is an iterator. If you try to call the next function directly on a standard string object, the code immediately breaks. The traceback tells us why. The string is a passive container. It lacks the _next attribute required to dispense values. The correct workflow requires calling itero first, generating a dedicated str iterator object that possesses the next function. If we create two different iterators from the same string, calling next alternates outputs, proving they maintain iteration state entirely independently. This strict separation of data and state acts as an architectural safeguard. It guarantees that multiple loops operating on the exact same list won't corrupt each other's progress. Building a custom iterator from scratch requires boiler code. You must write a class manually defining _init, _iter, and _next. You also explicitly track state, like an index marker, and write logic to raise the stop iteration error. This state management becomes a critical issue when we look at how standard data structures handle large data payloads. Standard collections like lists use eager evaluation. They force your system to load the entire dataset into RAM simultaneously before the iteration can even start. If you are a data scientist attempting to process a dataset with millions of rows, eager evaluation creates a massive bottleneck. Loading all of it at once will max out your memory and crash the system. This leaves us with a specific problem: how to process a dataset that is physically larger than your available system memory without writing massive verbose iterator classes to handle it item by item. The generator function provides an elegant built-in solution for creating iterators without the heavy boilerplate of custom classes. The core difference in syntax is that a generator uses the yield keyword instead of a standard return statement. Hitting a yield statement returns a value, but the function doesn't terminate. It pauses, preserving local variables in memory. Called again via next_to, it wakes up and resumes where it left off, generating the next item on demand. All the tedious class structure, the _iter and _next methods, and the manual stop iteration logic we saw earlier are handled automatically by the generator. Because this dynamic, lazy evaluation only generates elements when they are explicitly requested, generators are vastly more memory efficient than returning fully populated lists. Definite iteration in Python operates through a strictly orchestrated handoff of responsibilities. It starts with the iterable, a passive data repository. Through iter, we extract the iterator, the active, stateful agent dispensing data sequentially until exhausted. Within this hierarchy, generators provide a syntax-efficient pathway for implementing this iterator pattern. This entire complex pipeline is executing perfectly in the background every single time you type a simple one-line for loop. This architecture, separating passive data from active state, enables pipelines that process millions of records while maintaining a negligible memory footprint.